So we saw sampling last time. And I didn't quite finish the whole argument, but I think it's probably enough. I didn't want to finalize that whole argument this time. I wanted to kind of talk about some other stuff, but you should check out the notes and see that full argument. So kind of what I wanted to reflect on now is, when does sampling work well, right? When does sampling work well? Because, oh, yeah, question.
If we want to learn about all the measure theory stuff, do you have a paper you can post on Slack?
Yeah, good questions. Yeah, so the question is, if the measure theory sounds interesting and you want to learn more about that, where do you go? Yeah, so I think there's a book that I really love on measure theory, which I'll recommend. I definitely think a book is the way to go. It's called Measure, Integration, and Real Analysis. Measure, Integration, and Real Analysis. And it's by Axler. If you know linear algebra done right, it's the same guy. He made a really, really good book on measure theory. Like, this is a fabulous book. This is like my standard go-to reference on the subject. And he actually works through in a lot of detail the question of putting a measure on the countably infinite bit stream as an example. So this is a really good place to go and look. I like that book a lot. Yeah. So I guess kind of there's this empirical question of when does sampling work well and when doesn't it work well, right? Because we want to make systems for probabilistic programming languages, right? We want to actually make systems, and so if you give me a system that works by sampling, I told you that worst case reasoning is hard, computing the semantics is hard. So when does this one work okay and when doesn't it work okay, right? So the big question is, when does sampling work well? And I guess the other way to think about it is, when does it work poorly? Right? It's an empirical question. It's a question of, some examples it's going to work well and some it won't, right? So I guess one way to think about it is, here's an example. Here's a little program. I'm going to flip a coin, and the coin is going to have a really, really, really small probability of being true, right? A really small probability of being true. And I can flip another coin, and that coin will also have a really small probability of being true. And then I can, return their conjunction. Something like that. Right, so now you can imagine I'm sampling. I had to draw tons and tons and tons of samples, and here's what my samples look like. False, 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 false. Right, I'll get tons and tons and tons of false samples before I get a true sample. Right, and you can figure it out. You'll need, a million or something samples on average, before, probably more actually, before you'll see a true one. Right, so that seems like a bad case. Right, that seems like a bad case. So what is the tagline? So, direct sampling performs poorly for low probability estimates. And you kind of have the same problem if this is almost always true. Right, because you'll be getting true. It'll take a long time to get false. Yeah.
How big of a case really is this, though? Because I assume that when you get a result back from doing, say, n samples, what you're really saying is, like, we're giving you a range of probabilities, or an implicit range, on the order of 1 over n.
Yeah, yeah.
So if you do like 1,000 samples and you get 0, that's still like, if this is like
a
trillion, it's still in the range.
Yeah.
That's not bad.
Yeah, no, I think that's a very good point. So the point that's being raised is, isn't this okay? Isn't this in some sense morally okay? Because it's true that the probability of it being false is very, very small, right? And I think to a certain extent, as long as you're okay tolerating that, that's okay. But let me show you an instance where it's not okay, where you won't like it, right? And this is really where conditioning comes in. So I mentioned last time that conditioning and sampling don't play very nicely together, right? Briefly mentioned this, you might not remember it, but let's see an example. So imagine I have, let's change this program a little bit. Let's do this. Observe x and y. Return x. Uh-oh. So now you can imagine there's a version of sampling. How do we handle observe with sampling? We didn't talk about that last time. How do we handle observe with sampling? So there's a very straightforward approach, which is rejection sampling. It's one of these ideas with a good name, right? And what's the idea with rejection sampling? Well, it's pretty much the same as sampling, except when I get to an observe, if I violate the observation, then I'll just forget about that sample and draw another one, right? So maybe I'll sample, true, false, true, and then maybe I violate the observation, and I'll denote that bottom, right? And when I go to estimate my probability for my program, I'm only going to consider the accepted samples, the ones that weren't rejected, right? And so you can imagine this is going to take a really long time to sample something that satisfies that observation, right? It's going to keep drawing tons and tons and tons of samples, and tons of them will be rejected, right? And that's a problem. That's going to be really inefficient in practice, okay? So this is the low probability of evidence problem. And it's kind of the Achilles heel of direct sampling, is that if you want to be able to handle observations, well, sometimes you can have low probability observations. And then if I'm doing rejection sampling, I'm going to be throwing away lots of those samples, right? So if we want to be able to handle conditioning, we need to be able to do something better than this, right? And that's kind of the point of today's lecture, is to explore alternatives to sampling that aren't so sensitive to the parameters of the program, aren't so sensitive to the probabilities, right? Are there any questions about this? So this is really the downside of sampling, I think, at least of this strategy of sampling. So this is kind of like, if you're thinking about it like, the game we're playing so far is we have this fundamental worst case hardness of computing the semantics, right? And if you're willing to trade a little bit of approximation, then we can do sampling, which works pretty well in practice, especially if you're willing to tolerate some manageable amount of error. But it's really difficult to deal with sampling, with conditioning, right? Approximate is inherently a trade-off, and then conditioning is really tough, right? So we've found a little corner in our trade-off space here. Let's find a different one. And this is really, I think, the fun game when you're thinking about probabilistic programming languages, designing probabilistic programming languages, is finding interesting and profitable trade-offs that let you handle certain kinds of programs, right, and not hit this worst case behavior, and very carefully trade off some aspect, right? I think that's going to be kind of the game that we're playing, right? So what's an alternative to sampling? You've probably already been thinking about it. It's going to be based on search. Right? It's fundamentally based on search. Right? So I'll give you a little program. We'll have x, and then we're going to have, so we flip a coin for x, flip a fair coin for x. Right? Forgive me, I'm just going to use a probabilistic if Technically, this isn't in our syntax, but hopefully that's fine. You can agree with me that that's not too hard to define. Okay, and then I'll return z. Okay, here's my small program, right? First, I flip a coin. Then, depending on what that coin does, I flip one of two other coins, right? And then, depending on what this coin does, I flip one of two coins, and then I return the last coin in this chain. Right? Simple enough program. So I can represent I can write down, I guess, what you would call a search tree through this program, right? It would look something like this, right? So depending on what x does, I'll write solid lines for true x and dot dash lines for false x, right? And I'll put a number on these edges to denote the probability of taking each of those edges, right? And then, well, I'll branch on y, right? And then this will have, so we have to look at the program to know now what the probability on these edges is, right? So the probability of the edge for y, if x is true, well, that's 1/3, and then this is 2/3, and then if x is false, I have to look at the program and see that this one has 1/4, and this one has 3/4, right? And then I'll have z. And then this one will be 1/6. This one will be 5/6. This one will be if y is false, which is 1/7, 6/7. And then I'm going to do something similar down here. Okay, this one is again 1/6. Oops. Oh, and then the leaves, well, this will be whatever the program returns for this path, right? So in this case, it's going to be true, false. Okay, and then down here I have 1/6, 5/6, true, false. And then this is 1/7, and then 6/7. Right, I can draw this search tree here, yeah. Where did I do that? Here, yeah. Thank you. Great, so I can draw a search tree, right? And then using this search tree, I can compute the probability that the program returns a particular value. Once I've given you this search tree, what do? Well, I can kind of go the other way to compute the probability that the program returns a particular value, right? So if I'm at this point, I know that the program, so I wish I had another color. This is where having different colors is very useful. I'll kind of circle the numbers, I guess, right? So working inductively backwards, the circled number is the probability of returning true. Right, so I've labeled this root 1, this one 0, 1, 0, and so on. I won't label all of them. Okay, and then at this point, I can compute the probability that you return true here by looking at the probability that its children return true. Right, so in this case, I know that this one has a probability of 1 returning true, and I have a 1/6 chance of taking that path. So I can conclude that from this point, I have a 1/6 chance of returning true. Right, and then from here, similarly, I have a 1/7 chance of returning true. And then this is the interesting node where I have to combine the probabilities of the two children returning true. But I can do that by taking the products, right? So this node here, I need a little bit more room. This node here is going to get a probability of returning true of 1/3, the probability of taking this path, times the probability of returning true from that path, plus 2/3 times, it should be 1/6. What did I do? I'm at this node, right? So 1/3 times 1/6 plus 2/3 times 1/7. That's the probability of returning true at that node. Question?
So we're basically just computing the expected value of probability.
Yeah, I mean, this isn't expected. It's a sum of products. Expected values are sums of products. Right? So I can propagate this sum all the way back to the root. I'm not going to do that. That's a tedious exercise. But what you can see is that once I've got this tree, I've pretty much done all the work. Right? The tree has in it all of the data that I need to recursively compute backwards to get the probability of returning true for this program. Right? So this tree is nice. It's got all the data we need. But you might notice that the tree has some redundant structure in it. Right? It's got some redundant structure in it. If you look at the subtrees, right, in particular the subtree for Z, this top and bottom subtree, they're identical. Right? They're identical. Because, why are they identical? What's the reason for them being identical? Well, the reason they're identical is that Z doesn't depend directly on X. Right? All of the influence that X has on Z flows through Y. So if you look at the structure of this tree, you'll see that, of course Z depends on Y, but because it doesn't depend on X, we have like copies of it in the top and the bottom path because it shouldn't matter whether or not X was true. Right? So we could have drawn this tree in a more clever way where we reuse the duplicate substructure, right? We could have drawn it in a way that permits some kind of structure sharing. Right? We could have reused those duplicate subtrees. And then I can kind of do the same exercise where I compute the probability that this one is true, use that to compute the probability that this one is true. Right? But what's really nice is that this graph isn't growing too quickly. Right? You could imagine if I added a bunch more of these if statements, like maybe 50 of them. Each time I add one of them, it's only going to add one more layer to this graph, right? Like if I added a Q here, well, then I would have Q. It wouldn't depend on Y, so it would just come directly from Z. Right? So this graph is saving us a lot of effort. It's somehow finding the redundant computation and merging it into a single node. Right? So this graph is a very special kind of graph. It's called a binary decision diagram. And if we can somehow get at this thing, then we're going to be able to answer probabilities about this program very nicely, very efficiently, in the size of this graph. Right? Now, of course, the problem is, how do we build this thing? Right? Like, obviously, if I gave you this tree, well, maybe I can find the redundant subtrees and merge them or something, but then I had to build that tree. Right? It seems kind of tricky to get this graph without building that tree. Right? And there's very interesting tricks and strategies for doing that, which we're going to talk a little bit about today. By the way, how many people have heard of binary decision diagrams? A good chunk. Wow. Okay. So I'm hopefully going to give you a different perspective on it today. It's one of these data structures that shows up a lot. Knuth called these things one of the only fundamental data structures that's been introduced in the last 25 years, which is a pretty high praise. So he called this a fundamental data structure. And what's one of the really nice properties about them is that it's going to let us compute probabilities. But it does a lot of other stuff too. And we'll talk a little bit about what they let us do. All right. So the title of this lecture, I don't know if you noticed, was Tractability and Expressivity. What do I mean by tractability and expressivity? So, on the left here, I gave you a program, and I said, computing semantics, it's sharp P, hard. Okay? And on the right here, I've given you a graph. I'll call it a program, bear with me. And I said, computing semantics. And I really want you to think about this as a kind of probabilistic program, right? It can denote a probability distribution if I put weights on the edges, right? So if I make this weighted, 1/6, 5/6, and so on, then I can give this thing a semantics as a probability distribution given as the weighted sum of the models, right? And then I can say computing semantics is easy, meaning polynomial time in the size of the graph, right? I can simply propagate up and compute once for every node the probability of reachability, right? So over here I have a language that's nice and expressive, right? It has if statements. That's really expressive. We consider if statements expressive. Over here, I have a very, very, very restricted language. It's just like a graph, basically. But what I got out of it is tractable counting, tractable reasoning, right? Which I think is very interesting. So, this suggests a very fun design trade-off space between tractability. Let's put expressivity on this axis. Expressivity. And on this axis, we'll put tractability. Right? So down here, I have some very restricted languages, like that search tree that I drew you. I have binary decision diagrams I just showed you. There's actually other stuff over here too, which I won't have time to talk about, but I will hint at. And over here, we have this kind of nice set of tractable languages, meaning languages that I can compute their probabilistic semantics of in polynomial time. Polynomial time. Semantics computation. And then, as I add more and more features, as I make my language more and more expressive, less restricted, maybe I have tiny people here, and then maybe I have, crazy languages like Stan and Pyro, et cetera, up there, right? And you can start to fill in an interesting language design landscape where you have slightly restricted languages, and I'll put some others here too. One called Problog, has people, right? And you can start to fill in these like somewhat restricted but still more tractable languages which distinguish them from the general purpose, maybe even Turing complete languages you might want to put up here, right? And what this kind of suggests is a strategy for reasoning about probabilistic programs based on compilation. Hopefully you guys are already thinking in that direction, which is, I can take a program in one level and try to move it into another level, right? That might be useful. If I can do that, then I'll be able to compute the probability of this, if this is a semantics preserving compilation, by using whatever nice reasoning strategy I have on one of these more tractable languages. So I like to think of these tractable languages as like an assembly language for probabilistic inference or probabilistic reasoning. If you can get your programs into one of these things, then you're pretty much done. You can use whatever nice tractable reasoning argument you have over here to compute the semantics of your more expressive language. Now, of course, nothing's for free, right? Nothing's for free. Where did we put the cost? Right? Well, we put the cost in this arrow, right? This squiggly arrow I drew here might be expensive, right? But what we've gained is a very syntactic way of reasoning about the cost, which is very useful, right? I can think about, okay, well, this is a semantics preserving syntax-to-syntax translation. What does it do? What are its costs? When does it work well? When doesn't it work well? And you can start to study this arrow. And it turns out this arrow is much easier to understand than an arbitrary algorithm. Right? Compilation is pretty nice. We can reason about the cost of compilation much more easily than we can about, for instance, sampling. Right? I had to give you a very hand-wavy argument about sampling. I was like, well, it works well when it works well, and how do we know when it works well? Well, it's very empirical. Sometimes it works well, sometimes it doesn't. Well, here I'm telling you, look, if you can compile this thing into this thing, you're done. Yeah, question.
You mentioned a semantics preserving compilation. What if you're okay with losing a little bit of semantics, but bounding the error in a nice way?
Wonderful. Great idea. Good paper idea. Yeah, good paper idea. Yeah, we're going to talk about semantics preserving compilation for now. The question, by the way, was, what if I'm willing to not have perfect semantics preservation, but almost semantics preservation? And I think that's a wonderful idea. I don't know of any paper that's done that. So there's your free idea for today. Yeah. Okay. I don't want to work on the runaway board. It's too troublesome. I'll go over here. You know what? I have to. That's okay. Okay, so as you can tell, I really like this picture. I think we should fill in these languages more. And I want to tell you a lot about this one here, because I think this is like the starting point, right? If you can understand this one, then the rest of them look very similar. So let me tell you a little bit more about it. So I have to give a lot of credit for this idea to a particular person in a particular sub-area, which I doubt you've heard of. Okay, so there's this whole area of study called knowledge compilation. You probably haven't heard of it. But it even uses the word compilation, which I think is interesting, right? And I'm going to credit a very particular person at Darwish with really pushing this idea, right? And he had a very particular observation, which is that the hardness of reasoning about various tasks for a Boolean formula is very related to its syntax, right? So relationship between hardness of propositional reasoning tasks and syntax of formulae. When you think about it, it makes sense, right? If I give you a really, really restricted propositional formula, well, then probably SAT might be easy, right? Like, for example, let's say I give you a formula that's written in what's called disjunctive normal form, which looks like this. It's called DNF. And all of the formulas written in DNF look like this. A and B, or A and C and D bar, or they're written as a big disjunction of conjuncts. You have to write it that way. That's the only way. Okay. Well, then if I want to solve SAT for a formula that's written in DNF, what do? It's not a trick question. How do I find one assignment to this formula? Yeah. Yeah. Exactly. So if I want to find a model, an assignment to the formula that satisfies these constraints, well, I can just look at one of them. This is called a term. And then fill in whatever the other variables I want. I just know that as long as A and B are true, I'm done. That's a satisfying assignment. And I could look at the other ones and get another one that way. I look at that one and get the other one that way, and so on. Okay. So here's an example of a formula for which, of a family of formulae, right? The family of DNF, for which SAT is easy. Well, you all know that SAT is NP complete, so clearly SAT can't be easy for all formula, but at least for this one it is, right? So then this kind of begs a question, and it's a very nice question. What kinds of structure enable efficient reasoning? Very interested in this question, right? What kinds of structure that I put on these formula enable efficient reasoning? In this case, it's somehow the fact that it's a disjunction of conjuncts, which makes it easy to solve SAT, right? Now, are there other richer, more flexible kinds of structure, right? And Adnan, in a classic paper from '02 called A Knowledge Compilation Map, identified a bunch of cool structures and one of them is BDD, and kind of characterized the various kinds of tasks that are efficient for those structures. Right? Question?
What was the name of that paper?
A knowledge compilation map. Right. And in this paper, he gave some nice definitions for things that I really like. One of them was succinctness, which I prefer to think of as expressivity, which is kind of its inverse, right? Succinctness. Basically, he said, one language, a language L1, is more succinct. And think of languages for now, at least in Adnan's paper, as kinds of propositional formula. But, you know, maybe you can think of them as programming languages, right? That would be interesting. L1 is more succinct than L2 if it is efficient, meaning polynomial time, to translate all programs, meaning semantics preserving translation, of course, translate all programs written in L1 to programs written in L2. Okay. So you might be familiar with a classic paper from Matthias Felleisen on the relative expressivity of programming languages. And I think there's fun parallels between those ideas and some of the ideas from knowledge compilation, right? You know, we want to think about which languages can be efficiently expressed in other languages, right? Now, of course, if you think about this, clearly, you can start to make this figure less intuitive and more precise, right? When I say there's a separation between two classes, it means that these are more succinct than these, right? So I would say that BDD is more Tiny People is more succinct than BDD. More succinct, meaning I can write small programs in it, right? Okay. Any questions so far? Basically, I showed you an intuitive picture. And now, hopefully, we've made these axes much more precise, right? When I say expressiveness, I mean there exists an efficient semantics preserving translation between two of the same level, right? Question?
For the definition of efficiency, are we considering just in human terms, or do we just mean polynomial?
Let's say polynomial in the size of the program. Polynomial in the size of the program for some reasonable. I'm leaving this very high level, right? I think that actually taking this idea and making it precise is probably interesting research. Yeah.
For this translation, should we be thinking about like every possible, for instance, tiny DPL program being able to be converted to BDD, or should we consider like individual tiny DPL programs that might translate into BDD?
So in the context of this definition, this is saying this is a for all, right? It's saying it's more succinct if it is efficient to translate all, meaning like for all tiny people programs there exists a efficient semantics preserving translation from one to the other. Clearly this can't hold. Why can't that? Why? How do we know? Question, how do we know? How can we know? It's a simple argument. How can we know BDD is more succinct, than tiny people? How do we know? Yeah.
You can basically translate every single row of BDD into a tiny people variable and then return whatever's created.
I think maybe I didn't quite follow what you said, but I think maybe you had the other direction. I'm not. Maybe I misunderstood. What I was thinking was, if assume by contradiction that there exists an efficient semantics preserving translation from tiny people into BDD, assume there exists, right? Okay. Well then I know that BDD lets me compute probabilities in polynomial time. Therefore, I could follow the translation from tiny people into BDD. If this squiggly arrow is efficient, then I can run the semantics of BDD to get a probability. And if this whole chain is efficient, well, then I've just shown that tiny people has efficient computation for all programs. And that's a contradiction because we know that's Sharpie-Hart. Yeah.
So are you trying to say that BDD is more succinct than tiny people, or that tiny people is not more succinct than BDD?
Yeah, did I flip it?
Yeah, I think you're.
I think I flipped it.
Has it flipped in the bottom?
I always mix it up because I always think in expressiveness, and this one's the opposite. Yeah. So L1 is more succinct than L2 if it is efficient to translate all programs in L2 to L1. Yeah, there we go. Yeah. Sorry about that. Yeah. Expressiveness is the opposite arrow, and that's the one I usually think about, so I got confused. Yeah.
Are we not making any statement on the size of the compiled program?
Well, if it's efficient and it's therefore polynomial time, well, I can't generate one that's too big because I'm bounded. My space is bounded by my time, right? Yeah.
In the graph, is there anything that lives in the bottom left corner?
Wouldn't that be great? This is where I'll put, like, I don't know, we'll put a unicorn. That would be great. I think the game is more pushing things that way, right? You want to get there as much as possible, right? Now, I think you can fairly straightforwardly show that if I give you a Turing-complete language, well, then I'm not going to be able to. Wait, hold on, did I get it wrong? No, this is terrible. Why would you want that? You want this? This is very bad. Okay, yeah, no.
We kind of expect the top right corner to be empty, but I'm trying to wonder, does that also mean like the bottom left is also kind of empty?
Yeah, you wouldn't want to put too many things there, right? It would be a very inexpressive and very intractable language. So maybe, okay, here's an example of a very inexpressive and a very intractable language. Tables, right? Every single row in the table is a world, right? Well, it's very tractable, almost trivially, because the table's exponential in the number of states, right? And it's very inexpressive, because anything can be, this can efficiently compile into any other language, basically, because it's so huge that you'll be able to come up with an efficient translation from tables into, for instance, tiny people. Imagine how it would work, right? For each row in the table, I would generate a big if statement in the tiny people program that would pick out that row and flip a coin with the probability of that row, right? So I guess here we have tables. So, not a bad question, actually. I misunderstood it at first. Yeah.
Wouldn't that be very expressive?
Yeah.
Wouldn't that be very expressive? Because it can. No, expressive means that there exists an efficient compilation from anything into this. Now I'm confusing myself. It's very tractable, certainly. Is it very expressive? Now I'm off script. Now I'm just trying to figure it out on stage. Yeah. Oh, sure, yeah. Questions about expressiveness in terms of Kolmogorov and how do I talk about the size of things? Yeah, that's a natural notion of size, right? You could also use this number of AST nodes and so on. Another question, yeah.
Sorry, I know we've gone over this before. I just wanted what that question is on the board because it's going to drive me a little bit.
Yeah.
How can we know BDD is more succinct than tiny?
Yeah.
In other words, how can we know that it is efficient to translate all programs in tiny equal to BDD?
Yeah,
You've
yeah.
just shown that that is a contradiction.
You can't do that, correct. So then did I flip something again? Or is there a mistake over here?
What do you mean by, like, what do you mean, like, naturally by succinct? Like, what is a more succinct language?
So when I say a language is more succinct than another, what I'm meaning is that I can more efficiently write complicated programs in that language. Right?
So it's sort of like expressive?
It should be, right?
Like,
I keep confusing myself.
I think we need to say BDD is not more succinct.
yeah, that makes more sense.
Is not more. I think that's right. Okay. Whew. Somewhere in my notes is the answer, but it's kind of fun figuring it out, honestly. Yeah.
So is succinct similar to when we would say like terse or something?
Yeah.
Okay.
Yeah. 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 Right? Okay. Hopefully I had enough double negatives to thoroughly confuse everyone. Yeah.
Yeah, I'm also confused with the definition because now that we flipped it, it doesn't say now the same.
Let me give you notes. I'll give you notes where I fix it up. I hope we can agree there is an intuitive correct version of this. But now we've gone around enough times to where I don't know where we are. I'm sorry. Yeah.
Just to be clear, is it a contradiction or an open question?
It's a contradiction. So if you assume that it is hard to, if you assume that there exists a efficient translation from tiny people into BDD, that is a contradiction. Because we know that this thing, its inference is Sharpie hard. And I suppose that's open, whether or not Sharpie hard is in P. That's one of these open questions. It would be very exciting if Sharpie were easy. I don't think it is, but maybe. So this is up to the assumption that it is Sharpie hard. Cool. By the way, if you're confused about this definition, sorry, this is the most important thing, right? Like we're talking about the efficiency of this compilation. Once you understand the idea, you can come up with the right definition, right? Okay. I want to talk in some more detail about how we do this compilation. Right? Hopefully we understand the picture and where it fits onto this landscape and things. But now let's talk about how we actually do it. Compiling tiny people to BDD. Okay? We want to do that. We want to do this reasoning value compilation. So this is actually from a paper of mine from OPLSS 2020, but it's based on a bunch of ideas that are from other papers, right? Well, we need to think a little bit about how we want this compilation to proceed, right? And there's actually lots of ways of doing it, right? What I want is a compositional compilation, right? What I want is a compositional compilation, meaning imagine I have kind of picture this as a program, right? I want to be able to take pieces of the program, compile those pieces into some BDDs. And then I want to combine those pieces together to get one for the whole program, right? That would be really nice if I could do that, right? Because it would give me like a modularity to my compilation strategy. I would be able to reason compositionally about the cost of compiling this, the cost of compiling this, the cost of combining the results, and I would get some locality of reasoning to my cost and to my compilation, right? It'd be great if we could do this. This is going to rely on a wonderful property of binary decision diagrams, which is that you can take two binary decision diagrams for two smaller formula and combine them to get a binary decision diagram for the whole formula, right? BDDs have a natural compositionality. And I think the family of tractable languages that have compositionality to them are very interesting, right? I don't think we understand that very well. We only have a small bit of that picture, right? So BDDs have compositionality. So what do I mean? So imagine I have two BDDs. You know what? Let me get a big board. I'm going to do this on a big board. Okay. Okay, composing together two BDDs. So let's take two. Let's say we have a BDD representing A and B. All right, so this BDD represents the formula A and B. And hopefully you guys can agree, these are, remember, the solid edges are true, the dashed edges are false, and the leaves are labeled with the truth and falsehood of the formula, right? Okay, and now imagine I have another formula, which is A and, let's say, B bar, not B. Okay, so if A is true, then B needs to be false now. Otherwise, we get false. Okay, those are my two. Okay, and imagine I got this one by compiling one part of the program, right? And this one by compiling another part of the program, maybe. And I want to disjoin them. Maybe these are coming out of an if statement, for example. And I want to take the two branches of an if statement and combine them into one. So I want to disjoin these. Okay, or let's start with conjunction. It's actually a little easier to see. Let's do conjunction. Okay, so what do we do? So they both have, I'm going to show you a simple procedure. It's an inductive procedure. If you wanted to, you could actually write it using some inductive judgment style, but I'll just show you an example. So, you know, they both start with A, right? They're both starting with A. So what do? Well, I'm going to conjoin the true child and the false child together, right? So pictorially, what I'll do, we'll call this B1, we'll call this B2. If they share the same, what's called top variable, B3, B4, well, if I'm going to conjoin these together, what I'll get out of that, I'm going to do the following. I will now conjoin B1 and B2 down here. So this is going to be my step of progress. Or B3, sorry, B3. B2 and B4. Okay, so you can see how I've made progress, right? And the progress is that I'm going one step down the tree on both halves, right? So if you follow this procedure, and then of course we need base cases, right? So the base cases are true and anything is equal to B, false and B is equal to false. Right, so now I have a full inductive procedure, basically. Right? I can now kind of go down this tree, and for instance, to do the false half, what would I do? Well, I would go down the false half, and I would get false, and I would take their conjunction. That would trigger this base case to give me back false. So then I would get on this left half, I would get false, right? Right? So this is false and false, which is false, right? And then I would go down the true path, and I would take the conjunction of these two, right? Well, the conjunction of these two, well, then that's again inductive. I would take, did I get this? Yeah, I would take this conjunction, and I would take this conjunction, which would get me this BDD, false, false, right? Because true and you need to line up. I drew the edges kind of the wrong way here. Let me do this instead. Now you can kind of line them up, right? So it would be false and false, false and false, which gives me false, false. Right? So this is how I take two BDDs, combine them compositionally to get a BDD that represents their conjunction. Now we're not done. You guys are like, wait, you're not done. Because I haven't done something yet to this BDD. So there's a couple more steps.
Wait, when you redrew that tree,
Yeah.
the right tree,
Yeah.
and the conjunction,
Oh, yeah.
A goes to, yeah.
Good catch. Yeah. Yeah. Thanks. I don't know who helped me, but thank you. Okay. So there's a couple more things that we do. So BDDs have a couple of important structural invariants that need to be maintained. Couple structural invariants that need to be maintained for BDDs. One is what's called ordering, which means that variables need to be encountered in the same order along all paths, and at most once. Ordering of variables is the same on all paths. And then the other invariant is what's called reduction. Which is a two-step property. The first is that there are no isomorphic subtrees. And if you're thinking syntactically, no redundant subterms. Right? So if you have a redundancy, you have to merge them into a single pointer, essentially, right? And then two is no vacuous children, or vacuous nodes, which are nodes whose children are equal. So if I have a node, and then this is B1, and then its child is also B, right? Well, that's supposed to become just B. right? If it doesn't matter what A does, in either case you get B, you have to collapse it, reduce it. Yeah.
Isn't that the cost benefit first case because the two children are isomorphic?
Yeah, I suppose so. But you need to yeah, you're right. You're right. This is a redundant case, technically. Yeah. I hate to erase it because we're going to need it in 1 second. Because it's actually what you need. Because it's actually the inductive invariant. But, yeah, okay, you're right. This is technically implied by the first. All right. All right, so if you have no isomorphic subtrees, then and you have ordering, then BDDs have a very special property. These things together imply something called canonicity, which to me is one of the most interesting things about BDDs, which is that there is only exactly one structural BDD for a particular formula, right? So what does this mean? This is going to imply that if I have two formula, phi1 and phi2, with equivalent semantics as logical formula. I'm leaving this hand wavy, but you could imagine you give a semantics for logical formula in terms of possible worlds. Right? So if they have equivalent semantics, this is true if and only if they have equivalent syntactic reduced ordered binary decision diagrams. Phi1's BDD is syntactically equivalent to phi2's BDD, which looks a lot like the netcat kind of picture we had, which is a semantic equivalence implied by a syntactic rewriting theory, right? Which is actually very elegant, and this gives you a way of checking for equivalence between formula. Yeah?
This is assuming the BDDs have the same variable order?
Correct. Correct. Same variable ordering. If they don't have the same ordering, then they won't be syntactically equivalent, but there's actually a randomized algorithm for deciding equivalency, which is very interesting. So this is in BPP. Question?
So obviously this isn't relevant for equivalence, but for the conjunction, if they have different variables, what do you do?
Yeah, that's the other inductive case. I was missing that case, so I'll show you that one in a second. That's a great question. So I wasn't done with this one here. So this is clearly not reduced, right? So in order to reduce it, I will apply the rule that if two children are equal, then I just return one of the children. This is what I meant earlier when I said I'm going to need that rule, right? Okay, well then I need to apply it again, right? These are both false, so then I'm left with just false. And that makes sense, right? A and B and A and not B, that should be false. Right? So what's really interesting about this conjoin rule is that I can maintain a local invariant, which is merging redundant children, and get a global invariant, which is that there are no isomorphic subtrees. It's kind of a non-trivial proof, actually, to show that. I'm not going to go into that. So I actually gave you some code. So in GitHub, I gave you an implementation of BDD conjunction. I think it's really good to look at that code and see how you actually implement this, because it's quite interesting, and you can go in there and play with it and see how it works. Okay, so Shub asked about the other inductive case, of course. So let's do that one, and then we'll be done. Okay, so the other inductive case is if the top variables are not equal, right? So if I have like a and then let's say maybe this is the I know it's a little confusing. I'm using B circle for the variable and B triangle for BDDs. Bear with me. Okay? And I know in my variable order that A comes before B. Okay? Well then, I can't just go about conjoining these things, right? Because these are not compatible as Boolean functions. I can't just go about conjoining them this way. So what I do is I introduce a small rewrite. And if you want to, you can actually formalize this whole thing using a rewriting theory, which is kind of useful to do, actually. And then I introduce A, and I make it vacuous, but only for a moment. And then I have my B3. B3. Right? So now they're compatible, right? I can conjoin by propagating B1 and B, B2 and this B. Right? So clearly this is not reduced, but don't worry, it'll only be not reduced for a moment, right? Once we do the conjunction, it'll give me a different function, right? And then maybe it'll be vacuous and I'll merge it then, but this is how you resolve that case, is by introducing a temporary node like this, if you like. Of course, you don't have to do it this way, right? I could have written a separate inductive case where I just directly conjoined A with B and whatever. But it's nice to visualize it this way, I think, to understand how this works. Cool. Okay. Any questions? Any questions about BDDs? Great. Okay. Very nice data structure. Tons of very great properties. Gives me syntactic checks for equality. Gives me probabilistic computation. Yeah.
If you had an observe, do you use like a zero suppressed BD or something?
Oh, cool. Yeah. Question is, if I have observe, what do I do? Do you change the representation of your BDD to something called a zero suppressed BDD, which is fancy? You don't have to do that. You can actually use the fact that I can compute, like you essentially, I'm not going to get to the full compilation. I'll talk about that next time, and also its proof of semantics preservation. The trick is going to be that you're going to actually have two BDDs. One that represents the probability of accepting and one that's the unnormalized semantics. You do it that way. Or you could just count twice, once for the true and once for the false, and use the unnormalized semantics normalization trick. Could you use ZDDs? Maybe. Maybe. Cool. Okay. Let me see. Any other questions before I move on? Oh, lots of questions. Yeah.
So for just now, we talked about how no isomorphic subtree implies no vacuous nodes, but how about the case where a node looks like both branches point to the same thing? So there's no isomorphic subtree. So say it's just an A pointing in both true and false cases to false.
Yeah.
There's no isomorphic tree, but now A is vacuous.
So the isomorphic subtree in that case would be the false node.
But we don't have two subtrees, it's just a single tree.
Yeah. I get what you're saying.
Like a DAG.
So you're saying, what about this case?
No,
Or
there's a DAG, both point to one node. There's just one false node.
sorry, I can't quite picture. Come talk to me after. I'm happy to walk you through it. Yeah. And also, you can go and look at the code and see how we actually maintain this invariant. But yeah, it might have to do with the exact definition of isomorphic subtree, which I never gave you. Yeah. You need to be very careful about this. Yeah, it's true. I'm being a little hand wavy right now. Yeah.
I think the key to that question is saying you always have to have two coming out, one for true, one for false. Or like, you always have to have a solid and a dotted.
You always need to have two what? I'm sorry?
Like if you say you always need to have the solid and the dotted line coming out.
Hey guys, sorry, can you keep it down? I want to hear the question.
Then the question of only having one child can't happen.
Yeah, you always need to have two children. So maybe that's an answer. Yeah.
I think you probably also need that second rule because if you were to say the false is isomorphic to false,
Yeah.
trying to combine that, then you can't have two falses in the same tree at different places.
Yeah, there might be something like that. Yeah, I think you're right. Yeah. Yeah. Okay, cool. Yeah, there's all these little fussy things. I think, if we were writing it down on paper, we'd be very careful about these things. But I think in discussion mode, it's useful to think about which parts of these definitions you actually need and which ones you don't. It's actually a very good exercise, I think. Okay, cool. Great. So I'm pretty much at time, but I wanted to just kind of show you where we're going, right? So you're going to give me a tiny people program, right? And we're going to compile pieces of it into BDDs, and then use standard BDD composition operations to combine them, right? And you're going to get a lot of the benefits of modularity this way, right? Like if you can show that these two BDDs compose together nicely, then you can use structural properties of BDDs to argue about the complexity of inference for this program, which is quite nice because we understand BDDs a lot better than we understand, arbitrary inference. Right, so this is quite a useful reduction here that kind of makes it very practical for understanding. And also, we have very, very, very high performance BDD libraries. This is another thing I wanted to point out. There is really high quality code for compiling BDDs out there that people have worked on for many years. So if you can use these things to solve your problem, you're benefiting from a lot of engineering effort, right? Similar to like stat solvers in that way, right? And kind of the last thing I'll comment on is that, within this knowledge compilation picture, I drew a bunch of other stuff. D, DNNF, SDD, BDD. There's like a whole little world here of lots of different target representations, and the ways of compiling formula into them are very rich. Some of them use stat solver technology. I showed you only one way, which is what people call bottom-up compilation, which is you build one BDD by combining smaller ones. But there's actually lots of different ways of getting BDDs. You can do top-down, you can do a mixture of both, and there's different structures here that you can try to get to, right? So I think there's a lot of interesting surface area here for approaches to compiling policy programs. And hopefully there will be more stuff in this box. I think that would be really cool, too. Yeah. Any last questions? Yeah.
So you made this practical case, but speaking sort of non-morally, if you're just somewhat theoretical, is there a strong reason to do this? So we know that the compilation itself has to be non-efficient, but do we get a nicer theory from BDDs?
Certainly. Yeah. I mean, like, I don't know how far you want to go down. I mean, like, I've shown BDDs, but if you want to think of I think you can cook up a whole theoretical picture here that would be very exciting, which is like BDDs are terms written in an affine resource logic where things are consumed in the order in which they're produced exactly once, okay? And there's sharing of subterms, okay? That's an interesting theory. And I want to think about semantics preserving compilation between two programs into that theory. Like, I think there's a way here to make this exciting, right? Like, I think that, and then you can think about the theory of BDDs, right? Like, it's telling me things about my inference costs. So, how do I know about, I mean, I think there's something there, is basically what I'm trying to say. But, I think this is more the high level intuition to kind of show you why you might want to do this. Yeah.
I'm sure you know this. Are you letting us go 10 minutes early?
Oh, is it ending at 10:20?
Yeah.
Oh, I totally miscalculated. Oh, well then great. Let's finish up. Let's see. Okay. Okay. X gets flip 1/2. Y, we'll do a small part of that program I showed you earlier, right? Last time I had X, Y, and Z. let's just do this part of it. Okay. So I'm going to, let's do the simplest possible thing, which is sort of like an environment passing situation, I suppose. So I'm going to give you a compilation arrow, which looks like that. Okay, and it's going to take, on the left is going to be, we'll have terms in our language. I'm going to have an environment, and this is going to give me a BDD. Okay, that's going to be the structure of my relation. And in this environment is going to be a map from names to BDD. So this is just going to be an extra piece of data I'm carrying around during my compilation. There's a lot of ways you could write this compilation arrow. You know, actually in the old paper we had a different one. This one's a little easier. It introduces less data. And in the notes, or in the code, I actually gave you an implementation of this arrow. So you can play with this if you like. Okay. So what are we going to do? So we need to define that relation inductively, right? So the base case, and then this is going to be in any environment. Well, that's just going to compile to, I don't know, let's just say on the right side is a BDD, right? So I will make a new BDD node that's just true only if that's just true for this says this variable is true, right? And then I'll put weights on the edges, theta and 1 minus theta. Okay, so flip just compiles to that, right? And the inductive and the invariant that we want this compilation to maintain is that it's semantics preserving, right? Which is going to be that, like, you know, flip theta of true, and I guess technically you'll need a row, it has to equal the semantics of whatever this compiled to, right? F1, true, false, theta, 1 minus theta. This is just going to be just that, let's say. I didn't define this semantics for you, but it's the thing you expect, right? Which is like, it's the probability of this node is equal to theta times the probability of that node plus 1 minus theta times the probability of that node. So it's defined inductively in the straightforward way. So this is the notion of semantics preservation I want for this compilation, right? And here, hopefully, you can see that this is, in fact, semantics preserving. This is the base case, and it's straightforward, right? Okay. So then what about bind? I need more space. Okay. So environment row. What does that compile to? Well, I promised you this compilation would be compositional, right? So we're going to compile E1 in row to some BDD, right? And then now this row is a map from names to BDDs, so I'm allowed to do this. I can say E2 row where I add x becomes B1. That's going to compile to B2, and then this thing is going to compile to B2. Right? So first I compile E1 to a BDD. Then I stow that in the environment and compile E2 now with that in the environment. So whenever I want to get x, I'm just going to grab a BDD now. Okay? And then I need to define return. This one actually turns out to be the somewhat interesting case because I need to give a compilation semantics for pure terms. And this is where I start to have to give up some expressivity in my language. I need to be able to come up with a way of compiling pure terms into BDDs. Okay, so I need an extra rule, essentially, that lets me do something like this. Now, as long as my pure terms are a nice, restricted little language, it seems like I might be able to do that, right? If it's only got basically things I can do to BDDs, right? Conjoin them, disjoin them, their Boolean variables, and so on, then I should be able to do something like this. So let's see an example. So, you know, for my, did I keep my program? Yeah, perfect. Okay, let's compile this. Maybe I'll do it over here. Not enough time. Okay, so let me just quickly show you. How quickly can I do this? So what I'm going to end up having to do is it's if x. So, you know, the first step will be to apply the bind rule, which will be I'm going to stow in the empty environment. That is going to compile to a BDD, the one that I showed you, the base case, which is that. Right. Okay. And then I'm going to compile this sub-expression. That needs to get compiled in the context of x getting this guy. That's going to compile this. Right? And in the end, what you'll end up with is a BDD that looks like what? It'll be F1. If F1, then we're going to have two separate BDDs, this one and this one, right? And then it'll be 1/3 and 1/4. I got that right. This should be the final BDD you get in the end. Okay, question?
You mentioned there are multiple techniques to compile the BDDs, but you also present the canonicity theorem. Are these techniques different in an interesting way?
Yeah, they're going to have different runtime properties. Different formula will compile more efficiently using one technique or another. Yeah.
Even with the canonicity theorem?
Yeah, actually, yeah. I can talk to you more about that. It's pretty interesting. Yeah.
So does the compositionality of our compilation make it hard for us to identify the true and false leaves at the bottom of our BDD here?
Hard to identify the true.
The way we've represented it as a tree, whereas one might expect that at the two different F2 guys, you go down both to the same true and to the same false.
You're going to need to do merging for everything.
Oh,
yeah,
okay. So
yeah.
a more global kind of merging.
Yeah, it's a global merging. Yeah. Okay, great. So that was very fast. So I'll just kind of wrap up. So it turns out this is a really effective way in practice of doing inference on these things. Basically, you saw with that rule and these compilation rules a really, really efficient and effective way in practice of doing probabilistic inference on these kinds of programs, right? Which is pretty cool. 80 minutes is enough time to kind of see basically everything you need to yourself implement pretty close to a state-of-the-art, discrete, probabilistic program inference strategy. There's a few missing details, and I was rushing at the end, but you saw most of it. So hopefully now you can go and look at the code, and in that code is a small implementation of a language that actually implements these compilation rules. You can go and look at how that actually works, right? Like, you know, you can read the code, right? And you can play with it. And it's fun. I bet you will have a hard time writing by hand a program that isn't so fast that it'll terminate in less than like a quarter of a second. Like you have to generate big programs to not have them actually terminate very quickly with this strategy. Yeah.
What language construct in tiny people causes a hard compilation rule? Because somehow the compilation rules we have seen so far, they seem...
You're allowed to put an arbitrary Boolean expression there. That's the problem. So I can put like a big, ugly, nasty formula there that will require a bunch of BDD operations that are all end up making a large BDD. Right? So there's actually lower bounds and upper bounds on BDD size. There's a tremendous amount of theory about BDDs. There's a book by Knuth, The Art of Computer Programming. In the book, there's almost 110 pages on BDDs. And he proves like 35 theorems about different sizes of BDDs and has like 100 exercises on different sizes of BDDs. It's remarkably well studied. So we understand a lot about the size of these BDDs and how they're different nice formula and whatever. So it's quite interesting. Yeah.
So out of the two properties of the BDDs that you have, that like there's no perfect good subtrees and also there's some variable ordering.
Yeah.
Does the order of variables actually matter? And if it does, does it change things about the size of BDDs in certain cases?
Yeah, in order for this inductive conjunction step to make progress, you need to have fixed variable order. That's important.
But like, do different permutations of your variables give you BDDs that look drastically different?
Absolutely. Very sensitive to the variable size.
And are there like heuristics for choosing good?
Oh yeah, there's books on it. Books. I'm not kidding. Yeah, there's there's a whole science of picking variable orders and using various graph algorithms to find good decompositions and so on. It's actually very interesting. But we can't talk about that. So I should call it because we're told to end on time. So thanks you guys. I'll see you tomorrow for one more.